Hey, welcome to Unit 16, Solubility and Complex Ions. The main thing we'll be focusing on today is what we call solubility. It's learning how salts, especially salts that are not completely soluble, that only dissolve a little bit, learning more about how they dissolve in water. This unit's a little bit simpler than Unit 15, which I think will be a nice break because that unit is brutal. So to try to keep the video as short as possible, we're going to go ahead and get started. Talking about the solubility product constant and common ion effect. So, starting with solubility equilibria. See that word equilibria? It means equilibrium. It's just like the plural form. Solubility is the amount of a substance that dissolves in a given volume of solvent at a given temperature. So if I say the solubility of a salt is like 5 molar, that means I can dissolve 5 moles of it per liter. If the solubility of something is like way less than that, say like the solubility of lead chloride is like 0.002 molar. That means I can dissolve 2 moles of it in every 0.002 moles of it in every 1 liter. Okay? That's kind of what we mean by solubility. How much stuff will dissolve into a given amount of solution. When a slightly soluble substance, such as calcium fluoride here, dissolves into water, okay, our reaction, if we take a look at it, of calcium fluoride, CaF2, it is a solid, because we're starting with a solid. Remember, solids means they're not included in the equilibrium expressions at all, so we'll keep that in mind. Splits into its ions, into Ca2 plus, aqueous, and 2F minus, aqueous. But when it splits, the reverse reaction happens as well. The products also collide with each other and reform their reactant. So I produced calcium and fluoride, but they're actually going to reverse the reaction as well. The reverse will also happen, calcium and fluorine colliding into each other, making more of the solid salt. That's a fancy way to say that there's an equilibrium. Okay? CaF2 solid, because it doesn't dissolve 100%, it's not a completely soluble salt, will exist in an equilibrium with its 2 ions. We use the Ksp. So this is just like K, like Ka or Kb or Kc or Kp or Keq, a lot of Ks. But this is specifically for salts, and more specifically than that, for slightly soluble salts. The solubility product constant, Sp stands for solubility product. So if we have our equilibrium reaction here, CaF turning into its ions, for the reaction above, Ksp is going to be products over reactants, exactly like all other Ks, except our reactant, our only reactant, is a solid, so we don't include it in the equilibrium expression. Therefore, Ksp is just calcium and fluorine. Got to square it because I had 2 of them in my coefficients become the exponents there. Okay? Remember, pure solids are not included in the equilibrium expression. The measured solubility is the amount of solid that dissolves in solution. The amount of exposed surface area, stirring or grinding the solid, will only affect the speed of the reaction, not the position of the equilibrium. This is kind of pulling back to rates and equilibrium. The rates that a reaction occurs is not the same as the equilibrium. The capital K is different than little k. Okay. We're going to do 3 examples here. These are the main sorts of problems I'm going to ask you about solubility. So it's basically just going to look like this. We're going to talk about a salt. So here I have copper 1 bromide as my salt, CuBr. Okay. Has a measured solubility of this many moles per liter. What that means is this many moles of copper 1 bromide is able to be dissolved by 1 liter of water at this temperature. If you increase the temperature, you can actually dissolve more. Or if you decrease the temperature, you might dissolve less. So that's just kind of the set temperature. We want to calculate its Ksp. All right. So we have our copper bromide, CuBr. It is a slightly soluble salt because it has doesn't dissolve. It would say it dissolves entirely, if not. So I'm going to draw my really pretty equilibrium arrows here. It's going to split apart into its ions. It's going to split into 1 copper, because there's only 1 of them. I know it has a 1 plus charge, although it's not going to really matter. and then bromine 1 minus. I'm going to set up a little ice table. But for all Ksp problems, remember this is a solid. So I don't care about it at all. We are only looking at the products. Okay? Before it dissolves, I have none of this to start with. As it dissolves, I'm going to get plus x to both of these. And I'll be left with x at equilibrium of both of these. Okay? So that's kind of what's going on in this reaction. I'm taking my salt, it's going to dissolve a little bit. We're not exactly sure how much. I start with none of my two ions, add a little bit, and I have x at equilibrium. Okay? So a couple of things to keep in mind. Measured solubility, or sometimes called molar solubility. What it really means, it's the amount that dissolves. So in this example, it'll be the amount of CuBr that dissolves. Okay. Another way to think about it, though, is just whatever number x is, right? I don't really care about any of this. Its numbers won't matter because it's not included in the equilibrium expression, but x is just the amount of this that dissolves. So molar solubility or measured solubility is just x. Okay. So it says in the problem, I have a measured solubility of 2.0 times 10 to the minus 4. That is literally just x. That is the amount that dissolves. So I'm going to plug that into my two things here. And both of these would be equal to 2 times 10 to the negative fourth. That is how much dissolves. So I'm going to set up my Ksp. It's products over reactants. My two products are copper 1 plus and bromine minus over my reactants. Don't care about. Ksp doesn't matter. Your reactants won't matter. Plug in these numbers. 2 times 10 to the minus 4 for both. And then you're able to solve. A little more room. 4 times 10 to the minus 8 is our Ksp. That's the idea of these problems. Here's the whole thing. Okay. I have my salt dissolving into two different things. The molar solubility is the amount that dissolves. Okay. So both of these, I'll put the equilibrium values, which in this problem was 2 times 10 to the minus 4th, into my Ksp to find the Ksp. The Ksp is a value, constant for each salt, that tells you about how much of it dissolves. Okay. We have two more examples we're going to do back to back to show some different things that can happen in a problem. Next, I'm going to calculate the Ksp. So exactly what we just did. We're looking for the Ksp again. For another salt, bismuth sulfide. Okay. We've never really worked with bismuth before. Doesn't matter. Treat it like everything else, which has a solubility of 1 times 10 to the minus 15th. So this doesn't dissolve very much at all when you put it into water. 1 times 10 to the negative 15th moles dissolve into each liter of water you use. A liter of water is a lot of water, and 1 times 10 to the minus 15th moles is a very, very small amount. So this is only very, very slightly soluble. So what I'm expecting is my Ksp is going to be a pretty small number. It should be actually a very small number, and we'll see that as we go. So this is a hardly soluble salt, but it will dissolve just a little bit, because that's what equilibrium means. Okay. So, problem again. This time we have bismuth sulfide. They were nice enough to give us the formula. This is going to split apart in equilibrium with. Okay. This time it's going to make 2 bismuths. Because I have the subscript 2, every one of these that splits apart will produce 2 bismuths with a 3 plus charge. I know it has a 3 plus charge because when I made this compound, the 3 came from the bismuth's charge. Plus sulfur, I have 3 sulfurs. So I'll put a 3 in front of that. 3 sulfurs, which will have a 2 minus charge because that's where that 2 came from. Okay. Just like before, this one is a solid. I should have wrote it after, I just didn't leave myself room. But these 2 are ions, so you know they're aqueous. Like last time, I want to find the Ksp, which means I need to find the equilibrium values of the things we care about. Once I have those, I can plug them into the Ksp formula, get my answer. I'm going to start by writing my expression for Ksp in this problem. It's products over reactants, but we know the reactants don't matter. Products, I have bismuth, 3 plus, and remember to square it because of this 2 in front, because I have 2 of those. And then I have sulfur, 2 minus. Need to remember to cube it. That's my expression. I just need to now find these numbers so I can plug them in and then I can solve for Ksp. The other information given to me in the problem is the molar solubility, which is X. X equals 1 times 10 to the minus 15th. But be careful, don't just take this number and plug it in over here, because we have to think about the coefficients, how many ions of each are being made. We start with 0. This one's going to be plus 2x, because every reaction makes 2 of these ions. And this one's actually plus 3x. So that means x is this number, but I have to double it here and then triple it here. So this one's 2 times 10 to the minus 15th. This one would be 3 times 10 to the minus 15th. Those are the numbers I'm going to plug into my Ksp. Okay? So the bismuth number is 2 times 10 to the minus 15th squared. The sulfur number is 3 times 10 to the minus 15th cubed. So this is going to be an extraordinarily small number. I'm going to plug this whole expression into my calculator because all I have left is numbers. And I get an incredibly small number, to the negative 1.08 times 10 to the negative 73rd power, which is such a small number. That's 0.72 zeros and then a 1. So like that's essentially 0. You don't have to put that. You would still put this in your answer, but that's basically 0, right? Some things hardly dissolve at all, which makes sense because our molar solubility, this number, was really, really small as well. Whole problem there, so you can see it. All right, next problem is going to be related, but I think we're going to change it up just a bit. I'm going to give you the Ksp value this time. So the Ksp value for copper 2 iodates, something CuIO3 2, okay, is 1.4 times 10 to the minus 7. So I give you the Ksp value this time. So like the last 2 problems, that's what we were solving for. We're going to do it backwards this time. Okay. Calculate its solubility. Remember, solubility is X. So this time we're doing it backwards. I'm giving you the Ksp, you're solving for X. Let's see how that would look. Okay. Copper iodate is a solid. Put it in the right spot this time. It is partially soluble. Copper makes 1 copper, 2 plus, and it makes 2 iodates, IO3 minus. If you don't get these charges exactly right, it's not going to affect your problem. But if you mess up these, it will. Okay, so the coefficients here are really important. Right, so you're just looking at the subscript to see how many of each ion are made. Okay, so my Ksp is given to me this time, 1.4 times 10 to the minus 7. Remember that Ksp is products over reactants, so in this example, it's going to be Cu2 plus times IO3 minus, and there's a 2, so I square it. I'm going to set up my ice table. Get that one out of there, starting with nothing here. A little bit of this is going to dissolve into this, so I'm going to do plus x over here, plus 2x over here. And I'll get x, and then I'll get 2x. If I can find x, that is my answer. So I want to find this x or whatever x. They're all the same, right? X is your molar solubility. It's the amount of this that dissolves, but it's also just equal to x. So I have my Ksp. I'm going to plug it into this formula. 1.4 times 10 to the minus 7 equals. I'm going to plug in these x values in for their concentrations here. So I have x of this. I have 2x of this. But remember to square it. 1.4 times 10 to the minus 7th equals, simplify all of this, 2x squared equals 4x squared. You have to square both terms. And then times x is 4x cubed. Divide this by 4, and then take the cube root of it, and you get 0.0327 equals x. And that is its solubility. If you want a unit, its unit is molarity, or moles per liter. I can dissolve 0.0327 moles of copper 2 iodate in 1 liter of water. Those are the two really main types of problems. Either I'm going to give you the Ksp, and you're going to use this method to find x, the molar solubility, or we'll do it backwards. I'll give you x, you'll plug in these numbers to find Ksp. Those are the two main types of salt problems. There's one more third type. We have one more example to do in these notes, but we'll get to that in just a minute. That's the majority of what you need to know about this unit. A salt's Ksp gives us information about its solubility. However, we must be careful in using Ksp to predict the relative solubilities of a group of salts. Okay. So just because something has a higher Ksp than something else doesn't necessarily mean it's going to dissolve more. There's actually a couple of different cases. One, if the salts being compared produce the same number of ions, or number two, salts being compared produce different number of ions. And let's see kind of what that means a little bit more. So focusing on number one here. If the salts being compared produce the same number of ions, let's look at these three salts. All three of them, you'll notice, only have one silver, one iodide, one of each. This one only has one copper, one iodide, one calcium, one sulfate. Not looking at their charges or anything, just counting the number of ions. All of these are basically the same salt because they'll make the same number of ions when they dissolve. In this case only, you can use Ksp to directly tell which of these three salts will dissolve more. The higher the Ksp, the more it's going to dissolve in water. But that only works when you have the same number of ions being made. So the Ksp of calcium sulfate is the highest, right? The smallest negative is the highest. So it would be the most soluble. The next most soluble will be copper iodide, because the Ksp is lower, but not as low as silver iodide, 1.5 times 10 to the minus 16th. The larger the Ksp, the more soluble the salt is. If the salts being compared produce a different number of ions, you cannot do that little shortcut. So here I have three different salts. This one makes 2 ions total. This one makes 3 ions total. This one makes 5 ions total. For these, you cannot use the Ksp to directly compare how soluble they are. Okay. So all of these, you'll notice, are hardly very soluble at all. Okay. But you can't directly say that bismuth one here is the least soluble because it has the smallest number, because it makes the most amount of ions. So in this case, if you don't have the same number of everything in your formula, you have to go to the solubilities instead. So you do a little bit of math, find the solubilities given the Ksp like we just did, and then you compare those. with the thing with the highest solubility will dissolve the most in solution. So if you look at these, the highest solubility of these three is actually the bismuth, which had the lowest Ksp. And that's just because, remember, when we do Ksp, we have to square some things, cube some things, so the numbers get a little bit messy. The solubility of this makes this one dissolve the most, and then copper sulfate is the least, because it has the lowest number. Okay. The common ion effect is exhibited when the dissolving solution and dissolving salt have a common ion. We talked about the common ion effect a little bit in the last unit with buffers, but we're just going to mention it a little bit more. Let's talk about how you dissolve some salts in a couple different solutions. Let's consider the solubility of this salt, silver chromate. And here's its Ksp. I'm going to dissolve it in 1 molar AgNO3 and in pure water. So the first one here is in pure water. I'm going to take my salt, my silver chromate, dissolve it in water. This is exactly what we would normally do. Okay. 0 initial. This one's plus 2x because you make 2 silvers. This one's just plus x because you only make 1. 2x on each one. And then you can find the Ksp. Ksp equals this times this, 2x squared for whatever. Right? Do all the math. You'll need to copy it down into the spot on your notes, but I'm not going to go through and work throughout the whole problem. Basically, though, the answer is in pure water, x is 1.3 times 10 to the minus 4. What that means is that's how much of this salt will dissolve per liter of water, 1.3 times 10 to the minus 4 moles. That is in pure water. And we're going to compare that to, I'm going to dissolve it in a solution of silver nitrate. So in 0.1 molar silver nitrate now, you have a common ion. The common ion is silver. You have silver here, and you have silver here. So when you set up your ice table, you'll have an initial amount of silver here. So that's going to affect your answers a little bit. You're going to plus 2x over here because you make 2 silvers. Still just plus x over here. And then your equilibrium will be 0.1 plus 2x. X is just going to be a super small number. So you're just going to make it basically 0.1. This one is just x. Plug them into your equilibrium equation. And then x this time is much smaller. And that's the main idea. Don't worry about this example too much. We're going to do some of these in class. But the main idea is that if you dissolve something into something else with the same ion, if you make the common ion effect occur, for example, like we did here, dissolving something with silver into something that already has some silver, it's going to be way less soluble than you would expect. Okay. We'll do that in a second. But the reason why is actually Le Chatelier's principle. Okay. So adding in extra of this ion here, right, our Ag1+. If I add more of that, the reaction shifts to the left. Because of that, less of this is going to dissolve. Adding in a common ion will shift against the equilibrium. It'll still proceed to the right overall because it has to, because you don't have any of this to start. Okay? You don't have any of the chromate, but it will push against it, and it won't go as far to the right as it would have. Okay. Next problem here. Calculate the solubility of solid CaF2 and 0.025 solution. Okay. Last example for today. We're going to try to dissolve our calcium fluoride. It dissolves into a calcium 2+ and 2 F-. If we dissolve this into water, we will just set up our ice table like normal, make both these zeros, and proceed. But we're not dissolving it into water. We're dissolving it into a sodium fluoride solution. And there's a common ion here, being the F. I have an F here. I have an F in my equilibrium. So when I'm dissolving this salt into my solution, there's already some F's floating around in that solution. I already have fluorine ions and sodium ions, which sodium never really matters, right? But I have these fluorine ions floating around because this is going to break into Na pluses and F minuses. Because of that, I'm going to actually have 0.025 moles of this to start. Okay. And by moles, of course, I meant molarity, not moles, right? Because that's what it gave me in the problem. I have none of this to start, but I do have some of this, so that'll affect the problem. Plus x here, plus 2x here, x 0.025 plus 2x. I want to calculate the solubility of this problem, which, remember, solubility is just x. It gives us the Ksp. Okay. 4 times 10 to the negative 11th. That's going to equal our products. Ca2 plus times F minus squared. Plug in my values here. X 0.025 plus 2x. Because Ksp is small, just like before, we can get rid of that plus 2x. Anywhere you have plus 2x, plus x or minus x, remember that x, if it's a really, really small number, that'll basically just equal 0.025. And that's true. X is going to be a really small number here. So instead of writing all of that, it would make your math really, really hard. You put that number instead. Now instead, your math is actually really easy. Don't forget to square. Okay. I'm going to square this number, divide this by that number squared, and get x equals very small number, 6.4 times 10 to the minus 8. Okay, that is your answer. That is how much of this salt will dissolve, which is very, very small. If you'd like, you could do this problem starting with 0 here and see how much more will dissolve, and it'll be a pretty significant amount. If you'd like to test to make sure that this approximation isn't too bad, 2 times x, the expression this is this, right? 0.025 plus 1.28 times 10 to the negative 7th. Super, super small number. 1, 2, 3, 4, 5, 6, 1, 2, 8. This number would be 0.025, 1, 2, 3, 1, 2, 8. That's why we can make this approximation. This number is essentially just 0.025, right? All these zeros would just be rounded away anyways. And that saves us a lot of work with our math. So that's a good approximation to have. Got our answer here. Molar solubility. All right. Last couple things we're going to talk about real quick. The pH of a solution can greatly affect how a salt dissolves. A salt might dissolve really well in acidic solution, but not well in basic, right? Or might need to be near neutral to dissolve. It just kind of depends on the situation. For example, the equilibrium for MgOH2 will be affected by an increase in pH to decrease solubility. Remember, increase of pH means it's getting more basic. So let's think about why this wouldn't dissolve as well in a basic solution. In a basic solution, by definition, you have a lot of OHs already floating around. That's what a base is, a solution with a lot of OHs, hydroxides floating around. This solution isn't going to dissolve very well because it has a common ion, hydroxide. Okay? So this would actually dissolve much better in an acid than it would in a base. On the other hand, a decrease in pH caused by the addition of H+ ions will increase the solubility of this a lot because the OH- ions are being removed. If I dissolve this in an acid, like I said, it would actually reduce the amount of hydroxides here because they would bond together, make water, and go away. And it would actually push the equilibrium to the right for you guys. Yeah. So bases don't dissolve well in basic solutions because there's already hydroxides floating around, but they dissolve really good in acidic solutions, and vice versa. A similar effect occurs for salts that contain the conjugate bases of a weak acid. Consider this equilibrium. Silver, phosphate. It makes some silver ions, makes some phosphate. Okay? In acidic solution, there's an excess of H+ ions, which react with those PO4 3-minuses. This is a conjugate base of all the different phosphorus acids, according to this reaction. So because this is floating around, the H pluses that are also in water, are, especially in an acidic solution, is going to have a lot of H pluses, will react with that phosphate and get rid of it. So as you're making this, the PO4, your phosphate ions, are being taken away as they're being made, which is going to shift the equilibrium further to the right. So that means this salt can keep dissolving because all the phosphates are being taken away. Since this lowers the concentration of phosphate in solution, it increases the solubility of this salt. Similar reactions will occur for anything that's a conjugate base of a common acid or base. Sulfur, carbonate, oxalate, and chromate are all examples of ones that will do that. Any weak acids conjugate. Or the same thing would happen with the conjugate acid of a weak base. Yeah. A salt such as NaCl will not be affected by a change in pH. It has the same solubility, acidic or basic. And that's because kind of what we learned about. The conjugates of a strong acid or strong base do not react with water. Chlorine minus anion is the conjugate of the strong acid HCl, so it doesn't react with H+. Na plus is the conjugate strong base of NaOH, so it doesn't react with OH-. Neutral salts don't care if it's acidic or basic, it'll dissolve the same no matter what. Okay. The ion product is Q. We talked about K and Q before, comparing them. And the same thing kind of applies here with KSPs. Q is the initial conditions of your system. K are your conditions at equilibrium. You can compare Q and KSP to see if a reaction will occur or not based on the amount of ions you have floating around in your solution initially. Kind of like before, if KSP is greater than Q, when you calculate it, precipitation occurs, which means you make a salt. But if KSP is less than Q, it does not. I use the same sort of trick here that we used for KSP before. Put them in alphabetical order. If K is greater than Q, this makes kind of like an arrow pointing to the right. This arrow, imagine an arrow with a little tail pointing to the right, which means precipitation occurs, the reaction occurs. But if Q is greater, put them in alphabetical order again, the arrow points to the left, which means the reaction goes backwards. It doesn't occur. This example I didn't realize I had in here because my notes are messed up. I will do this one. We're doing 2 of these problems in our notes. We'll just do this one in class. I want to keep these notes as short as possible. That's our last problem. Didn't realize that was there. So we'll go do that in class. It's an interesting problem. We're basically seeing if something will precipitate or not, but that'll be good for this video. I'll fill out this one in class with you, and then we'll do the ones on our worksheet. This would be a relatively short unit, which is good because we just had that really a couple of terrible units. Okay. I hope some of the things here made sense for you. Look forward to your questions in class. Bye, everybody.